Okay, Chemistry 3202 Course Overview Review. Unit 2, Section 1, Lesson 2, Bronsted-Lowry Acid-Base Definitions. Okay, up to this point we've been talking about acids and bases, and we've been talking about an operational definition, which simply explains an observation, what acids do. Acids turn blue litmus red, they neutralize bases, they produce hydrogen when reacted with metals. Bases, BRB or B right back, bases turn red litmus blue. So these are operational definitions that don't explain why. Then we jumped into the Arrhenius theory, and he said that hydrogen was being produced. Anything that had hydrogen would be an acid, and we didn't like that. So we had to modify our Arrhenius theory to come up with the modified Arrhenius theory, which said that the acid actually reacted with the water to produce H3O+. And now all of a sudden we're getting into a situation whereby this little bicarbonate ion is causing us trouble, because in one situation we can show it producing H3O+ when it reacts with water. In another situation it can react with water to produce OH-. So is it an acid? Is it a base? How can it be both? So on the scene comes a couple of fellows by the name of Bronsted and another fellow by the name of Lowry, and they tried to solve this conundrum. So here we go. So these are the outcomes for the Bronsted-Lowry acid-base definitions. So this is the third theory in the line. There was operational, then it was Arrhenius theory, then it was modified Arrhenius theory, and now it's the Bronsted-Lowry theory of acids and bases. And what these guys proposed is they said, okay, we're going to call this the proton transfer theory. And proton, of course, refers to a hydrogen. All right, so the idea here is that it's going to be a proton or the hydrogen transfer theory. Okay, what they proposed was that an acid is going to be a chemical species. It could be a cation, it could be an anion, or it could be a neutral molecule. And the only condition is that this species has to lose the proton. So anything that gives away a hydrogen is going to be an acid. Give away, acid. Give away, acid. The other situation here is they said a base is going to be a chemical species. It can be a cation, positive charge, it can be negative charge, or it could be neutral. That's going to gain a hydrogen. Hey, that's different. So this guy, a base, is going to gain a hydrogen. So this is a little bit off the wall from what Arrhenius was saying. Arrhenius was saying that if it's going to be a base, it has to involve hydroxide. These guys are saying, oh, no, new theory. An acid is something that's going to give away a hydrogen. A base is going to be something that gains the hydrogen. And the idea behind this is that it's an acid-base reaction. And the idea is that if something is going to lose a hydrogen, instantly there has to be something out there, or spontaneously, instantly, there has to be something out there that's going to gain it up right away. Because remember what the physicist said about a proton? Too unstable to be by itself. It has to be somehow stabilized by association with water or whatever. So Bronsted-Lowry is saying, no, we don't need any of that. The hydrogen is never going to be by itself for any moment in time. As soon as it's donated from an acid, it immediately gets accepted by the base. All right, so it's going to be an acid, a hydrogen transfer, and it's an instantaneous transfer. So what these guys are saying is they're saying, hey, let's look at this particular reaction that we have written here, hydrochloric acid and water, and they're saying, all right, if the hydrochloric acid is acting as an acid, it's going to donate its hydrogen to the water, and what's going to happen here is the water is going to act as the acid because it's donating or giving away the hydrogen. The base is accepting the hydrogen, or the water is accepting the hydrogen, so it's going to act as a base. So what we end up with on the other side is the H3O+, because the water gained that hydrogen, and we get Cl-. Now, they come up with a new set of terms here. They call this the conjugate acid and a conjugate base. And basically what conjugate refers to is the new acid or base that's formed. Now look at the double arrow here. This is indicating that the reaction can reverse itself and go in the other direction. So this is where the conjugate acid and base comes in. Because if we were going to go in the other direction here, we somehow have to get HCl back. So in order to get hydrochloric acid back, this H3O plus now has to donate its hydrogen if we're going to go in the reverse direction. And therefore, the H3O plus now is acting as an acid because it's donating or giving away its hydrogen. The Cl minus is acting as a base because in that direction, the Cl minus is going to accept or gain the hydrogen. So we refer to this as the conjugate acid and the conjugate base. Conjugate being the new acid and base that's formed in the forward direction. Okay? So what Bronsted-Lowry are suggesting is that everything happens in pairs. So the HCl and the Cl is an acid and a conjugate base pair. They work together. The Cl's work together. And in this case, the water, H2O, is working together with H3O plus. So we would refer to these guys as conjugate acid-base pairs. Now we can look at a couple more examples here as we go. Here's another one. This guy is the bicarbonate one. And we're looking at this and we're saying, okay, let's make bicarbonate act as a base. Okay, we're going to make it act as a base. So that's going to have to attract the hydrogen. And it's going to get it from H2O. And in the process, what we create is what's called the conjugate acid and the conjugate base. Now, you notice how we're not referring to it as being a base simply because, you know, how can we have a base present here? There's no OH minus. Bronsted-Lowry says we don't need OH minus. The only thing you need to be a base is you have to be able to attract the hydrogen. So in this case here, this guy now is going to be the new base, conjugate base, because it has the ability to attract the hydrogen. All right, this guy now is going to be the acid because this is the one that's going to donate the hydrogen. Now you might say, well, why can't that one be an acid because that has a hydrogen present as well? Well, we're going to talk about that in the next lesson, referring to the strengths of these guys. But remember we talked about up here how these guys work together. The Cl's work together. Well, down in this particular example, we're going to have the carbonate ion working together. So the bicarbonate is going to be paired up with the hydrogen carbonate. And likewise, the water is going to be paired up with the OH minus. Because remember now, we can write water as HOH like that. So there's your OH minus built into the water. All right? So there we go. A few more examples here now. Here's another example, and this is the idea of ammonia. How can we explain ammonia as being a base? Okay, Arrhenius modified his theory to say, well, the ammonia is going to react with the water to produce OH minus and NH4 plus. Bronsted-Lowry are going to say, no, that's not what's happening here. What's happening here is ammonia is acting as a base because it's capable of attracting another hydrogen to make NH4 plus. That's going to be our pair. By nitrogen is working together, NH3 and NH4 plus, they pair up, they work together. At the same time, if I want to get NH3 back by reversing this chemical reaction, the NH4 plus has to give up that hydrogen. That makes it an acid. So if I wanted to reverse this, the NH4 plus would donate its hydrogen to the OH minus, and therefore the NH4 plus is a conjugate acid in the reverse direction, and the OH minus now is going to attract the hydrogen so that I get water back. So once again, the H2O and the OH minus are working together. They're conjugate acid-base pairs. And if you ask me, well, why doesn't this one give up the hydrogen? Well, if this guy gives up the hydrogen, then this guy has to accept it, and that's not going to work. Because remember now, in order to reverse this reaction, I want to get NH3 back. So this guy has to be the acid. Okay, here's another reaction. How about acetic acid with water? And in this case, we get CH3COOH, acetic acid, reacting with the water. Now, one of the important things about acetic acid is that it has multiple hydrogens here, and we're saying, okay, we know it's acetic acid, right? It's an acid here, but which of these hydrogens is it going to donate? And the answer to that is it's the acid in the carboxylic acid portion. Remember we did organic last year? And it's a carboxylic acid group here. And that hydrogen is the donatable hydrogen. These three hydrogens here are held very, very tightly by these covalent bonds. They're not going anywhere. They stick around. This guy here is very loosely held. It's in the carboxylic acid group, so that's the one that gets donated, and therefore we get OH, we get an O minus here, and the free hydrogen. So what's happening now is that that hydrogen gets donated to the water. So in this sense, the carboxylic acid is acting as an acid. The water is acting as the base because it accepts the hydrogen. It's gaining the hydrogen. And what we see on the other side, of course, is going to be the acetate ion and H3O+. And there we go. Now, if we look at these guys and say, well, which of these is going to be the acid? Well, let's look at this and say, I want to get acetic acid back. In order for this to be turned back into acetic acid, they have to work together. That guy is going to have to get that hydrogen back somehow. So that's going to be acting as a base. H3O+, that's the one that's going to give away the hydrogen. That's going to be the conjugate or new acid. And we can see that now the water is pairing up with H3O+. Because remember what H3O+ is? H3O+ is this guy. Their water that's been associated with the H+. Right? So that's why it pairs up with water, because water is in H3O+. There we go. Okay. Amphoterism. Now this is the business we got to try to explain. All right. Modified Arrhenius couldn't explain why bicarbonate could be an acid in one situation and a base in another. Now the Bronsted-Lowry theory, not a problem. They're looking at this and they're saying, hey, we're going to call this amphoterism. That's a fancy word. Okay. It's got nothing to do with terrorism or anything like that. It's not a new kind of terrorism. It's just amphoterism. Okay, and this idea is that depending on the situation that the species is put in, if it's put in a situation where it's with a stronger base, then the substance is going to act as an acid. If it's put in a situation with something that's an acid, then the species will take on the role of a base. So it has a dual role or a split personality type thing. It's capable of donating a hydrogen to be an acid, and it's capable of accepting the hydrogen to be a base. So let's look at a couple of examples, and we'll say, well, let's look at the first example here. In this case, OH minus, sodium hydroxide, OH minus is a very strong base, and again, we'll look at that in the next lesson or two about strengths of acids and bases. But in any case, OH minus is a very strong base. So when placed in a container with hydroxide, the HCO3 has no other choice but to give up its hydrogen to this OH minus. It's going to act as the acid under those conditions because OH minus is a great big strong base. What we're going to see on the other side is going to be some CO3 2 minus and H2O. Now, if I wanted to reverse this, well, the only one that can donate hydrogen is going to be the water, and again, I want to try and get HCO3 back. So in this case, the carbonate ion is going to be accepting the hydrogen, it's going to be gaining one, so this guy is going to be the conjugate base, and the water is going to lose an electron, a hydrogen, to be the conjugate acid. There we go. Can we pair these guys up? Well, it looks like the carbonate is a partnership. They work together. And again, H2O, we can look at it as being written as HOH. So there's my other partnership between the OH minus and the water. All right. Look at the one down below. We can say, okay, again, HCO3 is mixed with some H3O+. Now, H3O+ is going to be a very, very strong acid. That's if both of these can donate, this guy is the one that's going to donate because it's a much stronger acid. So in that sense, when paired with H3O+, it has no other choice but to act as a base, and it's going to gain hydrogen. So this time, the transfer of the hydrogen is in the other direction. What do we see this time? We're going to see some H2CO3 and H2O. And again, if I want to get my HCO3 minus back, then I have to give away the hydrogen in that direction, which now makes H2CO3 the conjugate acid and water is the conjugate base. This time the partnerships are very similar. The partnership is the carbonate ion right here with the bicarbonate and hydrogen carbonate. And again, the other pairing is going to be the H3O plus and the H2O. And we would refer to these as conjugate acid-base pairs. Okay? So in the first reaction, the conjugate acid-base pairs are HCO3 minus and CO3 minus, and OH minus and H2O. And in the second reaction, the conjugate base pairs are HCO3 minus and H2CO3. Right? But you notice that the carbonates are going together in each case. The water, the OH minus and the H3O plus go together. There we go. Okay, so amphoterism then, it also sometimes is called amphoteric, all right, because we're talking about a proton. So sometimes you might hear it called amphoteric. In order to be able to exist or to behave as an amphoteric species, it has to have at least one removable hydrogen. So one of its hydrogen has to be able to come off, and at some other point, they also be able to accept a hydrogen. So for instance, we want to be able to show how boric acid can be amphoteric or amphoteric by reacting it. We want to show both reactions here. So in this case, we can show it acting as an acid. Okay, and in this case, we're going to see this guy producing right there. It's giving up the hydrogen. Okay, and there we go. They're their acid-base pairs. Okay, now in order for this guy to be amphoteric, H3BO3 has to be able to accept a hydrogen, and it can't do it. There's no such thing as H4BO3, so that's not going to be amphoteric as it's written. Okay, here's another one, ethanamine, and in this case, what have I got done here? All right, the idea here is that the NH2 molecule is the nitrogen lone pair here is able to attract the hydrogen ion, and that's what makes it a base, because now it's able to attract the third one here to be NH3+. So what we're seeing then in this case is CH3, CH2, NH3+ produces OH minus. So in this case, it's able to act as a base because it's able to attract the hydrogen right here on the nitrogen. And in that case, the water acts as an acid. So we're showing that water can be amphoteric. Not so much these guys. These are not the ones that are amphoteric. H3BO3 can only be an acid. Ethanamine can only be a base. All right, but what we've just shown you is the fact that water is acting as a base in that reaction, and it's acting as an acid there. It's amphoteric. Another example, we can show how HSO3, hydrogen sulfite, is amphoteric. We'll simply show it reacting with a strong base, OH minus, and we can see that in this case it's going to act as an acid because OH minus is very strong. Okay, so there we go. It donates its hydrogen, and what we end up getting is SO3 2 minus and H2O. Okay, and then finally we can show it acting as a base because we can mix it with some H3O plus, which is a strong acid. So that guy's going to donate its hydrogen that way, and what we're going to get is H2SO4 and H2O. So we just demonstrated the fact that this guy can act as an acid or a base. Okay, and I should really write in what the others are behaving as. Here we go. So OH minus is acting as a base. H3O plus is acting as an acid. Okay, SO3 2 minus up top there, this guy has to be a conjugate base. It cannot be an acid because it doesn't have any hydrogen to throw away. All right, or I shouldn't say throw away, I should say transfer or donate, because you don't throw away anything. So this guy's going to be the conjugate base, which makes water the conjugate acid. And there we go. Okay, a couple of examples. All right, we want to be able to identify if something is amphoteric or non-amphoteric. We want to justify our choices. The first one we're looking at is H2S, and we're saying, all right, not a problem. I'm simply showing H2S being able to donate a hydrogen. That's not a correct way of doing it. But what I want to get at is the idea that, yeah, it has a donatable hydrogen there, but it's not capable of accepting a hydrogen. So by gaining this hydrogen, it's not able to do that. H3S plus doesn't exist. You will not find that on any acid-base tables. So therefore, H2S can only act as an acid. It's not capable of acting as a base, so therefore it's not amphoteric. In the case of the fluoride ion, well, first off, it doesn't have any hydrogen to donate, so it's not possible that F- can be an acid. It doesn't have anything to donate. But F- can attract the hydrogen here and act as a base, right? So F- can attract the hydrogen and can act as a base. So it's not amphoteric, it's a base. All right? So this guy up here can only be an acid. This guy here can be a base only. All right, let's look at another example. And we're saying, how about hydrogen oxalate? Okay, hydrogen oxalate, that's that ion. And if you look at hydrogen oxalate, that's this compound right here. There's a carbon with a carboxylic acid like that. And we've got another carboxylic acid on this side. So we've got a situation here where that hydrogen is donatable because it's part of the carboxylic acid. And we've got a situation here where this OH, this O- here, is capable of attracting the hydrogen. So we can be an acid on this side, but we can be a base on this side. So hydrogen oxalate can do both. And there we go. So this guy can be amphoteric. Okay, another example. HPO42-. Okay, well, this guy can be both as well. Because HPO42- can donate a hydrogen and leave phosphate behind, so it can be an acid. But it can also attract the hydrogen to be H2PO4, which is dihydrogen phosphate. And you'll see these on the acid-base table. And you can find all these species on the acid-base table. So this ion, HPO42-, is amphoteric. It can be both an acid and a base, depending on the conditions. And finally, another example. We're looking at the cyanide ion. So at first glance, the cyanide ion doesn't have any hydrogen, so it cannot be an acid. And we're looking at this and saying, well, it can't be an acid. But it can attract the hydrogen here to be HCN, so therefore it can be a base. So this guy can be a base only. So in order for it to be amphoteric, it has to have a hydrogen that can be donated, and it has to have a spot where it can accept a hydrogen. There we go. Okay, finished. Make sure you take advantage of our online tutors, the online content, and if you have any questions, don't hesitate to drop me a line in the discussion postings. See ya.